Thanks, Dave, for alluding to my talk. All right, so let's talk about writing badass malware for OS X or OS X. So my name is Patrick Wardle. I work at a bunch of acronym places, including the very office at Fort Meade where Dave used to perform all sorts of amazing shenanigans. He's actually quite infamous there. So currently I'm the director of R&D at Synac. So Synac does crowdsourced vulnerability discovery with vetted security researchers. We basically have freelancers, researchers all over the world who are hacking on our customers' IoT devices, websites, networks. And to let you guys in on a little not so secret, our customers' security really sucks. So we end up paying out a ton of money to our researchers for pretty easy bugs. So if this interests you guys at all, definitely check out synac.com. Kind of an interesting business model. All right, so before diving in, I think it's good to concisely define any possibly ambiguous English terms, especially since we're in Miami. So for the context of this presentation, when I'm talking about implants, I'm talking about persistent malicious code, not what you see on South Beach. When I'm talking about hooking, I'm talking about intercepting function calls, installing a detour or a hook. Somewhat similarly, I'm talking about a Trojan. I'm talking about a malicious program that pretends to be something that's benign or legitimate. Injection is all about getting code into a remote or an external process. And then finally is a backdoor, which is code that provides undetected remote control. Now, I will caveat that my wife helped me design these slides, so I hope they're not too offensive. I did have to censor some of the icons because I had this slide in another deck I presented, and apparently the boob icon really offended someone. So if you want an uncensored copy, see me after the talk. All right, so today's talk can be broken down into pretty much 3 parts. We're going to start with a brief overview of current malware on OS X, on OS X, kind of talk about the status quo and show areas that we can improve. The core of the talk is going to be all about how we can create better OS X malware. We're going to talk about some novel ideas for initial infection. We're going to talk about some new, stealthier persistence mechanisms. Talk a little bit about self-defense, how we can make our malware protect itself or detect if it's been detected. Then I'm going to briefly touch on some features, and then finally show how we can bypass all of Apple's and all third-party security mitigations. And then now this is Infiltrate. We don't have to talk about defense, so definitely stoked on that. All right, so I briefly want to first talk about malware on OS X. We're going to look at some recent malware samples. I think this is a good idea because this will kind of give us a good idea of the status quo, the level of sophistication, and show us where we can improve. Now, I do want to caveat this and say that there are obviously known unknowns, right? There might be a ton of really sophisticated OS X malware out there that we just don't know about. However, when I look at the Windows side of the house, I see a lot of advanced malware that is being detected. So we see Stuxnet, Gauss, the Equation Group. And these malware samples are generally not detected by the AV companies. They're detected by users that submit them to VirusTotal. They're doing some network analysis and see some weird traffic and then grab all the binaries, stuff like that. So I think that if there was a lot of advanced OS X malware out there, we would likely see some of it. So some of you might be thinking, why are we talking about OS X malware? What's kind of the big deal? Well, this is kind of an obvious statement, but Macs are really pretty much everywhere. Apple is now the number 3 vendor in the US, number 5 worldwide. And if you look at the graph, you can see that their market share in the PC market has essentially doubled in the last 5 years. A few weeks ago at their Spring Forward event, they talked mostly about the iWatch, but they also talked a little bit about their laptops, their MacBook line. And they released this interesting graphic showing that while the industry as a whole was contracting, that their MacBook sales were actually doing really well. So as you guys all know, obviously as any technology becomes more prevalent, there's going to be more attacks, more malware. So we're just going to see this with OS X as well. But wait a minute, Apple tells us that Macs don't get malware, right? They actually had this really funny quote, funny to me, on their website till a few years ago, saying Macs don't get PC viruses. I mean, technically they don't get PC viruses, but they wanted to imply that Macs are completely immune. But this is obviously not the case. Interestingly, the first in the wild computer virus that was detected was actually a virus that infected Mac computers. And since then, we've seen Mac malware flourish. It hasn't quite flourished as much as Windows malware, but in the last few years, we've seen 50 or so new OS X malware families. Some of them infecting companies like Apple, it's kind of embarrassing, Facebook, and even Twitter. Now, more interesting to me, we have seen cases where governments, the Chinese, have gone after specific users, for example, Tibetan nationalists, who have been using Mac computers, and they were able to infiltrate, no pun intended, or infect these Mac computers with OS X malware. So this shows to me that OS X malware is a reality. Macs can obviously be hacked, and the problem is just going to become bigger if we don't do anything about it. All right, so let's talk about some current OS X malware samples. So the first one I want to talk about is XSCMV. This was reported, I believe, end of last year by FireEye. They attributed it to APT. I think their marketing department just has like an APT stamp or something that they put on any report. In terms of the initial infection vector, they didn't really specify, but they kind of implied that it was phishing using older exploits. Their analysis revealed that it was pretty much a standard backdoor. It provided decent and sufficient features. So we can see things like it provided a reverse shell, the ability to screen capture, keylog, nothing super advanced, but got the job done. Now, in terms of persistence, it persists as a launch agent. Now, I'll talk a little bit more about launch agents and launch daemons, but they're basically synonymous to Windows services. So, sure, they'll give you persistence, but they're not stealthy at all, right? You have to create a new entry. They show it as a brand new external process, so if the user looks at the process list, they'll see a new malicious process running. Now, a few days ago, someone actually went back and was looking at this malware sample, and they found that it actually was exploiting the root pipe vulnerability to get privilege escalation about a year ago. So this was actually an O day at the time in the malware. So that was kind of an interesting thing. However, looking at a lot of attacks that originate supposedly out of China, we see this happen a lot where the exploits seem pretty good. They have some sweet O day they use to infiltrate the network, and then the malware they drop is really very amateur. For example, on the Windows side of the house, they'll install some known malware, something like Poison Ivy, and they'll persist using the run key. I'm like, why did you use this awesome exploit and then have this crappy malware? So again, we kind of see this here where the exploit in malware is pretty cool, but the rest of the malware is very inelegant, very amateur. All right, so another recent OS X malware sample is iWorm. Now, even though it's named iWorm, it's really not a worm at all. It has no autonomous spreading capabilities. Actually no spreading capabilities at all. In terms of its infection vector, it spreads via infected torrents, right? Everyone wants free Photoshop. So if the user downloads Photoshop, it's infected, runs it, they will be infected with iWorm. Again, this is a very basic backdoor, gives the attacker the ability to survey the box, download and execute other commands. So again, sufficient, but really not that advanced. Again, in terms of its persistence, it persists as a launch daemon. Again, this is really not stealthy. There's going to be a new malicious process that's running, so pretty easy to detect. And then the final sample I want to mention is WireLurker. Now, WireLurker is a little more advanced, and the media kind of was all about this because it was able to infect users' iPhones if they accepted an enterprise certificate. However, the component that was on the Mac, again, really not that sophisticated. It basically just provided the attacker the ability to survey the box. Now, while the media was like, oh my god, there's this amazing piece of malware out there that can infect everything, there's this great quote from the security researcher that basically showed the malware for what it was. So again, it had an interesting feature or two, but the rest of the malware, very poorly written, very easy to detect, very easy to prevent. So after looking at these kind of cutting-edge samples, these most recently known OS X malware specimens, we can definitely draw some conclusions kind of as to the status quo. So in terms of infection, they pretty much all rely on the user either downloading something like an infected torrent, or if they are using phishing, it's older exploits. So if you're patched and not doing anything dumb, you're really not going to be affected by these malware samples. In terms of persistence, they all use well-known techniques, which makes it super easy to both detect and prevent. In terms of self-defense, we don't see the malware really implementing anything to protect itself from analysis or protect itself from detection or removal. Stealth, I haven't seen any of them doing any advanced stealth or even pretty much any stealth. They pretty much just try to hide in plain sight and hope that you don't notice the 2 or 3 new processes that they create. In terms of their features, this is the one area where current OS X malware seems to kind of suffice. But if you dig into a little more, look at the features, you see that very inelegantly implemented, right? So if they want a reverse shell, they're not going to implement this in proc. They're just going to bind the shell to like a remote port, like they're going to spawn off NSH or something. So again, really easy to detect. And then finally, in terms of bypassing firewalls, antivirus products, personal security products, again, there's just nothing there. You don't see the malware trying to detect these products and then actively trying to mitigate them or bypass them. So actually, if you had a product like Little Snitch, which is just a firewall, it would catch all these malware samples as they make their outgoing connections. So overall, I like to give this malware kind of a grade of a C. As I mentioned, it's sufficient, but definitely very inelegant, amateur, and very trivial to both detect and prevent. So our goal then today is how do we improve the status quo, right? We want to get that grade of a C up. Apple is definitely renowned for making great products, so I thought we should try to make malware for Macs equally awesome. So as I mentioned, Macs are usually infected by Trojans. So these are very common infection vectors, similar to on the Windows side of the house. You see websites that either are shady or malicious or have been compromised, and then when the user browses to them, it tries to get them to, it coerces them to try to download and basically infect themselves. So we see things like fake installers, fake updaters, rogue antivirus products, stuff like that. Also, a lot of times if you go to like an adult or a porn website and before showing you content, it says, hey, you have to download this codec to watch the adult content. So I've been told. And then finally, in terms of eyeworm, again, infected apps, everyone wants Photoshop and stuff. So now, this does kind of work. Users are dumb. There's no patch for human stupidity. But Apple has kind of stepped up their game and implemented some anti-malware mitigations that are baked into the OS that attempt to protect users from themselves. And we'll talk a little bit more about those. But for example, Gatekeeper won't allow unsigned code to run, even if the user tries to get it to run. So this also isn't going to get you widespread infection. And for targeted users or computer-savvy users, these infection mechanisms really aren't going to cut it. So let's talk about an infection mechanism that's a little better. So we all do download software. Now, the Mac App Store is super constrictive. So if you want OS X Mac software, you pretty much go to the company's website to get it. Now, the problem is that this is distributed over HTTP. Obviously, a network-level adversary or an attacker could infect this download. Now, you might be thinking, all right, it's 2015, how much software is really distributed over HTTP? Well, it turns out this is my actual doc. We can see that about 2/3 of the software is distributed over HTTP. Now, the reason that most companies do this isn't necessarily because they are lazy and dumb. I mean, some are. It's more of that they realize, as do I, that there's a difference between securing your connection and validating whatever you download. And on OS X, there's a built-in mechanism called Gatekeeper that will verify all downloaded software. So all these companies depend on that. They're like, I don't really need to secure my connection because Gatekeeper is going to verify the digital signature. And if anyone has man in the middle of it, it will detect and block it. Turns out this is true unless we have a bypass for Gatekeeper, which I will talk about. And then if we do, this is a big problem because now we can infect essentially any download that's coming in over HTTP. So again, great infection vector, we can target a lot of OS X users. You might still be thinking, okay, Patrick, that's your doc. You're a computer security person. You're probably downloading a lot of software from source forge or random websites. Of course, it's not HTTPS. It's not secure. I was like, all right, fair. So I went and downloaded every single piece of OS X security software that I could find, and every single one of them was downloaded over HTTP. These guys are supposed to be the shining examples of security. Nah, really. Also, all of these apps, these installers require root when run. So again, if an attacker can infect these because they're all coming over HTTP, not HTTPS, when run and the user puts in their credentials, they've just given the remote attacker root on their box. All right, so that's infection. And I want to talk a little bit about persistence. Again, persistence is something that all malware pretty much strives, so that it's automatically executed every time the box is rebooted. As I mentioned, all existing methods are known and very easy to detect and prevent. So we have launch items, which are login agents and login daemons, and then login items. Now, if you look at the right side of the screen, you can see at the top right there's Mac Protector, which is kind of a rogue AV product. You can see that actually when it installs and persists itself, it installs as a login item. This will give it automatic execution every time the user logs in, but it also means that it will show up in a UI. Now, anytime you're running malware and it shows up in the UI in a list of like installed stuff, I mean, that's really lame, in my opinion. And then similarly, Wire Lurker, which again was this piece of malware that everyone in the media was like, OMG, this is amazing. It installs 4 launch daemons. So this means there's 4 new processes that are running on your box. So again, like 0 stealth. This is incredibly amateurish. So yeah, so current methods kind of suck. So let's talk about some better approaches, some stealthier approaches. So I'm a big fan of binary infection. Now I know this is kind of an old school method. Remember reading the 29A articles where they talk about all these cool ways to infect Windows PE files. And the reason binary infection was so popular is it's pretty powerful. So first and foremost, it's pretty stealthy. If you get all your viral code within the binary you're infecting, you don't have any other files on the file system, so you're not going to start any new processes. So this is pretty stealthy. It's also really difficult to disinfect. So all current OS X malware that I know about, to uninstall it or clean it, you just delete the binary and then delete its persistence registry key kind of thing. Really easy. Yeah, AV companies can do this automatically as well. Now, if you infect a binary though, it's going to be harder to disinfect. You probably can't do that automatically. So I like that as well. And then finally, you gain load time process injection. If you infect the user's browser, every time the browser starts, your code will be executed as well, which means it can access the user's passwords, credentials, and then also if there's a firewall installed, it's probably going to trust the browser. So if your code is within the browser, you're good to go. The problem is the OS X loader validates digital signatures at runtime. So here we can see we try to infect Safari. Run Safari, it's going to crash. So obviously, this is not ideal. So if we look at how secure this mechanism is, we can see that the way it works is that the OS loader, whenever a binary is executed or an application is run, it checks for this LC code signature block inside the binary. And then it verifies the binary signature, so it can detect if it has been manipulated or modified. Recall, though, that unlike iOS, on OS X, unsigned applications are allowed to run. So what we can do is we can simply remove this signature from the binary, and then the loader will allow it to run, even though it was previously signed. So the loader has no concept of state. It didn't say, hey, this used to be signed, now it's not, I should block it. So here we see we can hash Safari, and then we run a little Python script that unsigns it and injects some malicious code. We then rehash Safari to show that it's changed, and then we open it. Again, we might expect that the loader would block this, but no, it turns out it allows it to run no problems. All right, so now we can infect away. So there's a myriad of ways to infect mock-O executables. You can do things like hijack the entry point. You can add a new dependency. So there's really pretty much limitless options. And again, the benefits here are that it's all self-contained. There's going to be no new processes. It's somewhat difficult to detect. And then finally, again, difficult to disinfect, which is a feature I like for malware. Probably my favorite OS X persistence mechanism is dilate hijacking. The reason I like this so much is if you have a vulnerable application, all you have to do is drop a specially crafted dilate to the file system, and it will be automatically run every time the application is started, either by the OS or the user. So this is very conceptually similar to DLL hijacking on Windows. Here you can see in the diagram, we basically have an application that has a dependency, and if this application is vulnerable, the situation exists where the loader will look in various locations for the dilate. Now, if the legitimate dilate that the application really wants is in a secondary search directory, for example, a system directory, and the loader looks somewhere else first, an attacker can plant or drop a malicious dilate in that primary search directory, and then every time the application is run, the loader will naively and blindly load the attacker's malicious dilate, so we get persistence that way. So what makes an app vulnerable? Well, there's two scenarios. The first scenario is if it has a weak dependency and that dependency is not met. The attacker can then place the dilate where it expects that weak dilate to be, and then the loader will load it. The second scenario, a little more complicated, but turns out it's actually more common. There's these dilates called run path dependent dilates, and basically it tells the loader to look in multiple locations. So again, if the primary run path search directory is empty, the attacker can plant a malicious dilate there, and then the loader will pick it up. So you do need a vulnerable application to trigger this, but it turns out there's a ton. This is a scan just for my box. There's about 150 of them. You can see that Apple has a ton of them. Word, their Office products as well, which I think it's kind of funny because they were vulnerable to DLL hijacking on Windows. Now they're vulnerable to dilate hijacking on OS X. And then also a lot of third-party ones, Google, Adobe, Dropbox, stuff like that. So in terms of persistence, this is an example of how we can use dilate hijacking to gain automatic code execution every time the box is rebooted. So there's this Apple app called the iCloud Photo Stream Agent. It is automatically started every time the user logs in, and it is vulnerable to a dilib hijack. So what we do is we simply configure our hijacker dilib to make sure it's compatible to the dilib we're hijacking, and this just ensures that symbols are still resolvable and nothing else kind of breaks. Then we copy this dilib to the primary run path search directory, and then from then on, anytime the box is rebooted, our malicious dilib will be automatically loaded by the OS, by the loader. So the benefits for this are, it's kind of a novel technique, so that's always good. It results in no new processes. Again, the user is not going to see anything amiss if they're just looking at activity monitor or something like that. No binary or OS modifications. This is nice. We're not breaking any digital signatures. We're not modifying any auto-run plist or configuration files. We're just dropping a dilib. And then again, we're abusing legitimate functionality of OS X. Anytime you can do that, it means it's going to be difficult for this technique to be patched out or detected because you're just kind of doing something legitimate. All right, so as you guys can tell, I'm kind of a fan of persistence mechanisms that don't create new processes. Again, stealthy, you're hosted in the context of a trusted OS X process. These are all kind of good things. So let's talk a little bit more about other ways we can get code inside processes. Well, it turns out on OS X, there's a ton of system processes that support plugins. An example of this is Spotlight. Now, Spotlight is a service that does indexing for you on your Mac. So when you hit Apple key spacebar and search kind of pulls up the results. Turns out you can extend Spotlight, basically to index custom files. So that's what we're going to do. So you can do this pretty easily. In Xcode, there's actually a template for a Spotlight importer. That's just the name for a Spotlight plugin. So you create that, and then you set the plugin match type. This basically says, this is the type of file I'm interested. Please load me and invoke me anytime this kind of file is accessed by the user. So if they edit it, they open it, they print it, anything like that. So if we create a Spotlight importer and then just drop it into the the library Spotlight folder, every time now the user accesses a type of file that we've registered for, our plugin will be loaded and then will stay resident in memory. The benefits, again, no new processes. It's kind of on demand, which I like. So if there's an AV product that's scanning all the running processes and dilibs every time the user logs in, our dilib, our Spotlight importer, is probably not going to be loaded yet. So that's cool. It's also cool because it provides you kind of a data sniffer feature capability. Think about it when you get on a box. If you're gathering intelligence, you probably want to grab all the user's documents. The old school way is scan the whole file system for Word docs or Pages documents, grab them all and exfil them. There's going to be a ton of documents, and a lot of them are probably not going to be relevant to the user. However, using this technique, if you register for, say, Pages documents or Word documents, you will just get the documents that the user is actively editing, reading, stuff like that. And again, this is legitimate functionality with the OS, so kind of hard to protect against or detect. Now, in this case, we are registering for Objective-C source code files, but you can basically register for anything if you want something that's a little more deterministic, or if the user is not, for example, a developer. So if you use public.data as your match type, your plugin will get automatically loaded when the user logs in. All right, so that was slicker, stealthier persistence mechanisms. I now want to talk a little bit about self-defense. Basically ways we can protect our malware from analysis, from detection, stuff like that. And I always wondered why malware doesn't employ more self-defense mechanisms. I guess on the Windows side, you see some anti-analysis, encryption. But on the Mac side of the house, the malware we see really doesn't have a lot, if any, self-defense. We see some crypto, but it's mostly in the command and control network traffic, and it's really easy to, it's usually like XOR or something kind of like. So the problem with this is this makes it way too easy for the antivirus companies. It makes it trivial to find and detect the malware. It makes it trivial to analyze, and then trivial to disinfect. So the AV guys have it really good. So let's talk a little bit about some self-defense, starting with how to protect our malware. Now I know there's a lot of ways to do encryption. It was a great talk about that this morning, but I just want to mention some other ways as well. So I generally think that encrypting one's malware is a good idea. It makes it less likely to be detected and also harder to analyze. So we're going to start with a simple method, but this method leverages the fact that OS X, the OS X loader actually supports encrypted mock O binaries natively. So that's kind of cool. So here's the loader source code. You can see that basically as it's loading the various segments, loading it into memory, if a segment has an SG protected version 1 flag, this indicates to the OS X loader that this segment is encrypted, and then OS X will automatically decrypt the segment. You should note, though, that it skips over the first 3 pages, so we'll address that in a second. So Apple uses this encryption to protect some of their binaries. For example, Finder, the doc. And if you try to load these into IDA, you'll get a warning saying that the code is encrypted. A little more information about this. The encryption algorithm is Blowfish, and they use a hard-coded static key. And since Blowfish is symmetrical and the key is static and hard-coded, yes, there are tools that can automatically decrypt this. However, I didn't see any tools that could automatically encrypt it. So I wrote a little tool that you can give it an arbitrary mock O binary, and it will encrypt it using Apple's encryption algorithm. Again, the benefit of this is you can then run it on any OS X box, and it'll be encrypted, but automatically be decrypted by the OS X loader. Remember, though, the first 3 pages aren't encrypted, so we want to make sure that nothing sensitive is in that, so we actually have to go back to the source code. So I found the easiest way to ensure that there's no sensitive information in these first 3 pages is just to create a function at the start that's aligned to a 3-page boundary. If we then lock that to the front of the segment using a symbol ordering flag, basically the first 3 pages are just going to be null or blank. So that's kind of cool. So here we see our little mock O binary. We compile it, we run strings, we can see all the methods it's calling, its strings. It's really easy to triage, kind of see what it's doing. If we then encrypt it and then run strings again, we can see that everything is encrypted. So, cool. Also, if you take known malware samples and encrypt it with this technique, you get about a 50% drop in detection. So that's, again, free and easy. Again, OS X supports that natively. But it's static encryption, so tools and some AV tools can automatically decrypt and detect. So I want to talk about an encryption scheme that's a little stronger, and basically will tie your malware specifically to your target. So I like this because a lot of the analysis reports you see, especially about more advanced malware, it's not that the AV companies detected them originally. You always see, 6 months ago, a user uploaded a file to virus total and had 0 detections. And then the AV companies do all sorts of crazy back-end analysis in the cloud, and then they discover, oh my goodness, this is the equation group, or this is some really exciting new nation-state malware. So I want to talk about how we can, though, hopefully prevent that. So one good way to kind of tie your malware to a box specifically is to use environmental keys. Now there's a research paper, Environmental Key Generation Towards Clueless Agent, that describes this. So we have various mathematical constructs. You have N, which is an environmental observation that should be unique for the target. We then have a one-way hash function. We then have M, which is the hashes of that observation N. And this is what is needed for activation so that the malware knows it's on its original intended target. And it's carried or embedded in the agent in the malware. And then you have K, which is just static encryption. So at runtime, what the malware does, it requeries its environment, and then it gets this observation N and double hashes this. If the double hash matches the embedded double hash, it knows that the single hash is its decryption key, so then it can decrypt. Now the benefit of this is if you choose a strong activation environment that is not easy to replicate, if the malware is ever taken off the box for analysis, for example, loaded to the cloud, the AV companies will not be able to decrypt it unless they can get access to the original target, which may be possible, but definitely raises the bar. Because, again, the malware doesn't know how to decrypt itself unless it itself is running in its intended environment. Now, this isn't a novel idea per se. I mean, we've seen this on the Windows side of the house. The Equation Group, some nation-state malware that I don't know anything about, does this. All right, so we have this nicely encrypted binary. It's either going to be stored on the file system encrypted, or it's going to be downloaded from a command and control server. However, either way, since we're using custom crypto, we can't depend on the OS X loader anymore, so we have to basically write our own loader. Normally, on the Windows side of the house, you would have to write your own custom loader. And you have to do things like mapping the image in, loading dependencies, link everything in. I'm sure a lot of us have written PE loaders in shellcode, right? It's doable, but it kind of sucks. Well, it turns out, though, that OS X supports in-memory loading, which is awesome. So yeah, so OS X makes it really easy to execute file images directly out of memory. Apple even used to host sample code about this. They no longer do, but if you Google memory-based bundle, you can find it online. So this is how we load a file image that we put into memory just using APIs. So first we call it ns create object file image from memory. This creates an object file image. We then link it in, look at our symbols, get the address of the symbol, for example, the exported function you want to call, and then you can call it. So here we have in-memory loading thanks to Apple and its APIs. So again, cool kind of technique. Again, it's free. It's kind of built into the OS. You should definitely use it. Now, there's a myriad of other ideas that malware could utilize to protect or defend itself. I just want to briefly mention 2 others. So first, I think that malware should make it harder to delete itself. As I mentioned earlier, all current OS X malware, to delete, you can just, you as a user or an antivirus product can just go and delete the binary and then delete its persistence entry, which is usually just deleting another file. So I thought, we should make it a little harder to actually delete the malware sample. So if we use the change flag command with the SCH flag, we can actually create a binary or a file that cannot be deleted unless the user boots into single user mode. So, obviously some users will be able to do this, but this is unlikely that antivirus products will be able to do this automatically. So again, not impossible, but just raises the bar, makes it difficult to automatically disinfect malware. The other thing that I haven't seen malware do, which I just think it should, is monitor itself. The worst thing for malware is to be detected. So I think malware should basically have some capabilities to detect if it's been detected. On OS X, there's a variety of ways you can do this. You can monitor the file system via dtrace or FS events. These will both give you real-time file system access. So if you're a piece of malware and you see someone copying yourself to a USB drive or CDing into your directory, that should be a big red flag, and you should, nuke the box, delete yourself, format the hard drive, something. Don't let them copy yourself to that USB drive. Similarly, again, as I mentioned, all these reports about awesome nation-state malware, I'll generally start with someone uploaded a random file to virus code. I'm always floored by why malware lets itself be uploaded. Because again, these are just normal users. These aren't, so they're probably uploading it from the box that it's on. So again, I think malware should have a self-defense, self-monitoring component that doesn't allow itself to be uploaded anywhere. If it sees itself uploaded, stop that connection, delete itself right in the box. And then finally, I think this is kind of a neat idea. I think that as malware authors, we should register the hashes or strings of our malware as Google AdWords, of course with a ton of other legitimate hashes. If you guys are like me, anytime we get a binary that we don't know what it is, I jump on Google, I Google the hash, I Google the strings, and if someone had registered a Google ad for that, that would trigger an alert. And so, if I had done this and then I see, someone in Russia Googles my hash, I will get an alert. Granted, they've already found my malware, but I can hopefully then go and clean off the rest of my targets. And I'll have known that they had been detected as opposed to waiting for a report from this person. All right, so self-defense. Now let's talk about some features. Now, I mentioned that most OS X malware that's currently out there has sufficient features. So I'm not going to spend a ton of time talking on this. However, I do want to mention process injection. This is a feature that's really powerful that I don't see a lot or any OS X malware utilizing. And also online sources or publicly available documentation is either outdated or broken. So I briefly want to talk about how to do this. So again, here we're first going to start talking about runtime process injection, talking about how we can get an arbitrary dialog into an external or remote process. As mentioned, the Mac Hacker's Handbook describes this, but it's only for 32-bit code. And then the OS X Internals website has a snippet of code describing how to do this to inject into 64-bit processes, but the code is buggy. I reached out to the author and he said it's intentionally buggy, but we're all adults here, so I think we can handle this. All right, so the first step is to know the target, know the external process you're injecting into. Now, all the online resources I found don't mention this, but obviously, operationally, this is very important. If you're injecting shellcode into a remote process, you have to know if it's 32-bit or 64-bit. Turns out this is pretty easy. If you call the proc PID info function and you give it a PID of the external remote process that you're injecting into, it will return you this structure with information about it, including a member in the structure that has a flag if the binary is 64-bit. So this is awesome. Most of Apple's apps are 64-bit, but a lot of third-party applications that you still might be interested in injecting into are 32-bit. So Google Drive, Dropbox, VPN apps, stuff like that. All right, so here's the shellcode we're going to inject. Now this is just from the OS X Internals website. This code actually works. So it does three things, pretty simple, could be more advanced, but gets the job done. So the first thing it does is it calls pthread set self. And this promotes the injected mock thread to a fully compliant POSIX thread. Now this is important to do because most APIs expect the thread to be a POSIX thread, and if it's not, they will crash. So this is the first essential step. We then call DL open to pull in our dilib that we want in the remote process. This is very similar to calling load library on Windows in a remote process to pull in your DLL. And then we just sleep to let the malicious dilib, or do whatever it needs to do. Again, you can do other stuff, but this works. So in order to inject and get the shellcode to execute, there's 5 things you need to do. The first thing you do is you call task for PID. This gives you access rights to the remote process that allows you to allocate memory and create remote threads. We then allocate memory for both the remote stack and for the shellcode that we're copying in. We then copy in the shellcode. Step 4, then we change the memory permissions to make it executable. And then step 5, we call thread create running to kick off the shellcode in the remote process. So here it is in code. I fixed this code, so this should work. We can see our steps that I just mentioned, calling task for PID, remotely allocating memory, copying in the shellcode, and then we set this thread structure with RIP, stack address, stuff like that, and then finally call that thread create running to kick off the remote thread. So now our dilib will be pulled into the remote process, and we'll have process injection. Now, runtime process injection is nice, but there are some downsides. First and foremost, you need an external persistent component that's monitoring. Say you want to inject into the user's browser, right? You have to have another piece of malware that's persistently installed, that will be automatically running, that will be waiting and watching for the user's browser to trigger the injection. So that's just more components, more complexities, more things to be detected. It's also a touch complex. You're doing process injection, shellcode. I mean, not that hard, but a little more complex. And then it's also pretty easy to detect. Generally, there's no good reason why process A should be remotely allocating memory, copying in code, and creating remote threads in process B. So again, pretty easy to detect. So I wanted to briefly mention and look at load time process injection. We can actually use dilib hijacking again to gain load time code execution whenever a process is started by just dropping a dilib. And again, this technique suffers from none of the complexities that runtime injection. So Xcode is a great example. I thought it would be an attractive target for malware. Maybe malware could use it to infect all deployed binaries, kind of as an autonomous propagation vector. Just wait until the developer compiles, the final product, and then if the malware is, basically in the compiler, it can inject some code in and kind of go along for the ride. So since Xcode is vulnerable to a dilib hijack, we can configure a malicious dilib and just drop it into the primary run path search directory. And now every time the user starts Xcode, the malicious dilib will be automatically loaded. So this is, Ken Thompson's idea, reflections on trust. Do you trust the compiler? If you can't, you're kind of screwed. And again, load time process injection is nice. We just have to drop a dilib. We get code execution within the target process. All right, so now let's talk about bypassing security products, both Apple's and third parties. So you can have the most sophisticated malware in the world, but if it gets caught, it's kind of game over, which, if you spent a ton of time developing it, that sucks. So I want to talk about bypassing, as I mentioned, security products starting with Apple's. So currently, all known OS X malware is detected, is thwarted by Apple's built-in anti-malware mitigations. Things like Gatekeeper, Xprotect, Sandbox, stuff like that. So Apple loves us because they say, oh, our Macs are so secure, we have all these great features that will proactively protect you. Unfortunately, we can bypass all of these trivially. So let's talk about that now. All right, so let's start with Gatekeeper. Now remember I mentioned that basically everyone distributes software over HTTP. They all count on Gatekeeper to verify the download, which seems somewhat reasonable. Also, Gatekeeper does a great job blocking malicious downloads. So if it's unsigned or from an untrusted user, Gatekeeper will actually block the binary even if the user double clicks it, kind of protecting the users from itself. But we want to bypass this. We want to be able to man-in-the-middle connections, distribute malware without Gatekeeper detecting this. So let's first look at how Gatekeeper works. So anytime you download something on a Mac, it gets flagged with this quarantine attribute. Then at runtime, if a binary has this quarantine attribute, Gatekeeper gets automatically invoked. Gatekeeper then checks the user's settings. For example, it says, has the user only allowed code from the Mac App Store, or does it have to be signed? And then we'll verify to make sure that the binary conforms to the user settings. And actually, Gatekeeper does a good job. As I mentioned, it does block malicious or infected downloads. Or if there is a man-in-the-middle attack, it will detect that the digital signature is no longer valid and block the connection. So it turns out the Gatekeeper does a great job verifying the downloaded application, but only that. It does not verify external content that's in, for example, the zip file or the DMG file that you're downloading. This normally isn't a problem unless the application loads that external content. So this is what we're going to do in 3 steps. So step 1, we're going to find an Apple-signed or Mac App Store approved application that contains an external relative reference to a hijackable dilate. We're then going to create a malicious DMG or zip file that we could deploy, or we could inject into an existing download, and that has this legitimate app that's vulnerable, and then also the necessary folder structure to contain the malicious dilate in that external reference location. And then we're going to make fun of Apple users, myself included. All right, so step 1, we need to find a Gatekeeper-approved application that has this external dependency. So instruments.app fits the bill. It is a developer tool that expects to be installed under Xcode, which is Apple's IDE. If we look at its dependencies with OTool, we can see that it tries to load a dilate from an external location, which makes sense since it's under Xcode. At runtime, it goes and looks for dilates in Xcode's shared framework folder. So what we can do now is we can create a malicious DMG zip file. Again, this is something that we could inject into an existing download. At the very top, you can see that we have instruments.app under this application folder. And then we have this external folder layout. This is what mirrors Xcode. This is what instruments.app expects. And then we can see we create this core simulator framework folder, and we put some malicious code in. So this is the dilate that we're going to hijack. Now, if a user would see this, if they downloaded a DMG and double-clicked and saw this, they would be like, what is this? What do I click on? This looks weird. So we got to clean this up a little bit. So let's hide all the files and folders we don't want. Let's set a top-level alias, so there's a nice big icon for the user to click. Let's change that icon, change the text, change the background, pretty much make it more believable. And then finally make the DMG read-only so that when the user double-clicks, it'll pop up for them to run. So if we do this, this is what we get. If you're downloading a Flash installer and you got this, I would probably click on that. Maybe take out the NSA logo, but other than that, it's pretty convincing, right? So again, we have Mac's Gatekeeper settings saying only allow code from the Mac App Store, no matter what. And then we have our malicious DMG file that could be hosted or injected into an existing one. So when the user downloads this and double-clicks it, there will be a standard pop-up. But this pop-up is for any downloaded content. So if we didn't inject, or this DMG was not malicious, the user would still see this pop-up. And again, the attack scenarios are getting the user to download a Trojan or inject into an existing download. So they're going to see this pop-up regardless. If they click open, even though our malicious dilate is not from the Mac App Store, it gets run. So we've just bypassed Gatekeeper. Now, we are running in the context of instruments.app, but our dilate gets code execution before the main function of instruments. So the user is not going to see instruments app pop up on the screen, right? Dilate will probably kill that, persist, and then kick off the legitimate Flash installer or whatever software they're running. So it should be completely transparent to the user. The other cool thing about this is Apple can't revoke the certificate for this. This is an Apple-signed binary we're using, so if they did, that would be problematic. All right, so that's bypassing Gatekeeper. Pretty cool. Let's now talk about bypassing XProtect. So XProtect is Apple's built-in AD product, and it detects and deletes malware, again, protecting users. So today, if you went and tried to download a torrent that was infected with iWorm and ran it, XProtect would protect you. Turns out, though, that XProtect is a very basic AD signature-based tool. If you look, here's the signature for iWorm, and you can see it's based on a hash and a file name. Lame. So this means that you can either just recompile the binary, or if you're writing new malware, which you probably will be, you won't even have to worry about XProtect, or you can just rename the file, and it won't detect it. Apple, yeah. So the other, another Apple technology we have to protect users is the Apple Sandbox. Now this is actually a fairly decent technology. I think it's because it's built on top of BSD's mandatory access control framework. So Apple didn't really write it, so I think that's the reason it's kind of secure. So Sandbox apps are apps from the Mac App Store or some of Apple's native applications. I think like Mail.app might be Sandbox. Again, Sandbox obviously prevents applications from accessing system components. So from a malware's point of view, this is something we want to escape. Well, it turns out our friends at Google are constantly releasing OS X kernel bugs that can be used to bypass the sandbox. So as long as they keep releasing bugs, sure be able to escape this. All right, so the last Apple security mechanism I want to talk about is their kernel mode code signing requirement. So to protect the kernel from unsigned drivers, rootkits, stuff like that, starting with Mavericks, all kernel extensions, or KEX, have to be signed. If an unsigned kernel extension is loaded or a modified one is attempted to be loaded, it'll be blocked. Now, this is not a novel security mechanism. On Windows, Vista 64 and above, the same kind of thing. So, and actually, it's a pretty good idea. So if you look at how this is all implemented, if you use a command like kexload, which is the command line tool you use to load a kernel extension on OS X, what it does is it sends an IPC mechanism to this user mode daemon called kexd. Kexd is in charge of loading the kernel extension. If we look at its source code, because it's open source, we can see that it is what is verifying the kernel mode kex signature. So this means that the signature is verified in user mode. So obviously, an attacker could just inject code into kexd, knock out or patch out these kernel checks, again, because it's in user mode, and then the unsigned kernel extension would be allowed to load. So this is what we do here. I did this in a debugger just for illustrative purposes. Again, you would probably use runtime code injection to realize this. So we inject into kexd, we disassemble the check kex signature function, and then we basically change the disassembly so it always returns 0, which means that the kex that we're about to load is signed, is okay. So if we do that, now we can use kexload to load unsigned kernel extensions. Really easy. Well, it turns out there's actually an even easier method. So remember I mentioned kexload is the utility you run to load the kernel extension. Turns out that if kexd, the user mode daemon that actually loads the kernel extension, is not available, so if it's been unloaded, kexload will try to load the kernel extension directly. So on Mavericks, they did not check the kernel extension's digital signature, so you could just unload kexd and then run kexload directly and it would load your unsigned kernel extension. So I mentioned this Apple was like, hey, you guys might want to fix this and your whole signature scheme's broken anyways. Their solution was to add signature checks to kexload in user mode. It's like, you serious? So what we can do is we can either patch kexload, or again, it's open source, so just download the source code, comment it out, recompile it, and then at runtime, unload kexd, run your patched kexload, and it will load your unsigned kernel extension. Of course, you could also directly just talk to the kernel syscalls that load the kex, because they're not doing any code verification. It's all done in user mode. But having a tool that does all the extra error checking stuff, kind of nice. All right, so Apple's built-in anti-malware mitigations are a complete joke. So hopefully third-party ones are going to secure this, right? Well, turns out that most of them, pretty much all of them, are all signature-based. So if you're writing new malware, which we probably will be, or attackers probably will be, they will be trivial to bypass. However, some, like Little Snitch, are more behavior-based. Little Snitch specifically is just a firewall. So it's going to be agnostic toward the malware. So, having new malware, it'll still detect it. So let's talk a little bit about Little Snitch, because it's just so widespread. I run it on my Mac. I know pretty much most of my friends do. So again, it's a firewall, just blocks untrusted outgoing connections. So our goal is simple. We want to be able to talk to the network in an uninhibited manner. Basically, we want to completely bypass Little Snitch. So Little Snitch takes a binary approach. It trusts known process, and it also allows the user to create blanket rules. So on my box, GPG keychain is allowed to talk to any endpoint on the network, on the internet. This kind of makes sense because it talks to key servers, checks for updates, stuff like this. Turns out though that GPG keychain is vulnerable to a dilib hijack attack. So as an attacker, we can just plant our malicious dilib in this primary search directory. We don't need root to do that. And then anytime GPG keychain is started, either programmatically by the attacker in the background or by the user, our malicious dilib will be loaded into the context, the process space of GPG keychain, and will be allowed to create any outgoing connection. That's awesome, but what if the user doesn't have GPG keychain? Well, it turns out that Little Snitch has an undeletable system rule that says anybody can talk to iCloud. Now, I don't know why they have this in here. Maybe they think that because computers are normally synced to a single iCloud account that an attacker couldn't abuse this, but we'll abuse this. So if we reverse engineer the iCloud protocol, with the goal of being able to upload or download files and commands to an attacker's iDrive without Little Snitch complaining. So if we look at the protocol that iCloud speaks, it turns out it's a JSON protocol. It's a lot going on, but really not that complex. So, and since it's JSON, pretty easy to read. So in order to exfil a file, it only takes 4 steps. First thing we do is we generate a login request. This just authenticates us against the attacker's secondary iCloud account. We then init an upload request, which gives us a URL for where we can then post the file to on iDrive, which is under iCloud. We then upload the file, and this then returns us a receipt and a wrapping key, which we then pass to the final API, which just commits the transaction. So I've implemented this in a Python script, and this allows anybody to talk directly to a secondary iCloud account to push files, download files, execute commands. And Little Snitch does not complain. Now, this is in Python, but you could programmatically implement this in any malware, and even if it was standalone, unsigned, untrusted, because Little Snitch has that undeletable system rule, it would let you through. So kind of completely bypass Little Snitch. So I kind of wanted to put everything together, design an end-to-end attack to kind of realize some of the things we talked about, but then also to test these third-party security products, see if any of them detected that. So here we have a little malware. I wouldn't say it's badass. It's still pretty simple, but we'll see, proves to be effective. So it's deployed as a malicious DMG or malicious zip file, or again, if you have network level access, if you own some routers or on your network and you can see these insecure downloads going by, you could inject this into legitimate downloads. Again, we use the gatekeeper bypass to get around gatekeeper to run unsigned code, even if the user has set it to only allow code from the Mac App Store. When the user runs it, we persist via a dilib hijack, so code will be automatically executed every time the user logs in or the box is rebooted. And then we exfil some files to iCloud, and then we download and run some commands. So to me, this kind of simulates what most malware needs to, wants to, requires to do. And again, you don't need root to execute this attack. So the test was simple, but I think pretty realistic. I would download the latest version of the AD product, the security product, the firewall product. Again, these are all over HTTP, complete fail, so I could have been infecting myself, but I did it on a VM. I then would run the AD product to install it and allow it to update so it had the latest signatures. And then I would run the downloaded unsafe.dmg file, which would infect my box and kick off the endpoint. So the test, I try to skew toward the personal security products, the AD products. And I said that if they detected and blocked any of the components of the malware, that would be a win for the AD product and a fail for the malware. So this means if it detected the malicious DMG, if it detected the gatekeeper bypass, if it detected the persistence, if it detected the exfiltration, if it detected the download, if it detected the execution of the command. So I did that, no real surprises here. None of the OS X security product detected any component of this malware. So not that surprising, but we've just exposed or re-exposed or confirmed the ineptitude of a multi-billion-dollar industry, right? But I'm sure you guys are ready for that. All right, so wrapping things up. This showed you current OS X malware, known samples out there, really lame. Super easy to detect, super easy to prevent, just very amateur. However, hopefully I've shown you guys today, provided some inspiration, some techniques to improve OS X malware. So we talked about ideas for infection, how we can bypass gatekeeper to do man-in-the-middle attacks. Some slicker persistence mechanisms, so more likely that we won't be detected. Talked briefly about some self-defense, talked on some features, and then also showed how bypassing personal security products, whether they be Apple's or third-party, is actually really trivial to do. So before we get to Q&A, I just briefly want to mention my OS X security website, Objective-C. This is not a shameless plug. Well, it kind of is. But the reason I'm mentioning it is it has a nice collection of known OS X malware samples. So when I started getting into OS X security, malware, I found it really hard to get modern samples to analyze. The AD companies don't want to give me malware samples. They're like this college, high school clique where you got to be in it to get access. So I spent a lot of time getting these samples. So all the malware I mentioned in this talk is available for download for free. I'm also putting security tools, again, all for free, that I run on my Mac to secure myself. So currently there's just one. It's a dilib hijack scanner. It'll tell you if applications are vulnerable or if you've been hijacked. And then next week I'm talking at RSA. I know it's kind of lame, but my boss says it's good for customers or something. I'm going to be releasing some other free security tools. Again, these are what I run on my box, just hopefully stay a little more secure. So check it out. If not, no big deal. So thank you for your time. I think we have 5 minutes, 2 minutes left. Email me, Twitter. The slides should be available for download. My company's on the West Coast, so I don't know if they're still awake yet, but if not, they should be there posted later today. So, do you guys have any questions? Dave says people ask really hard questions, so.
Stop. Nice stop. For the process injection part, OS X has this notion of the initial thread. So when you're trying to inject code into a new process and you create a new thread, if it just so happens that the dialog that you load from that new thread brings in, let's say, core foundation, then the process is going to die. It's going to get killed immediately because you're not supposed to initialize core foundation from a different thread other than the initial thread. So I'm just wondering if you ran into this issue and how you dealt with it.
Yeah,
It's very common.
that's a good question, because also when I develop security tools, if they're running in the background and you try to do something on a background thread, yeah, if it's a UI or anything like that, it'll crash. So what I do to bypass that is I use dispatch async, and you can actually run code on the context of the main thread, or perform selector on main thread. So there's APIs that basically says, hey, please run this code on the main thread. And I'll schedule it in a run loop so that it's not blocking the main thread. I mean, obviously you don't want to do something that's really intensive because it will block the main thread, but if it's something quick, you can execute code on the main thread. But yes, that's something to be aware of, because otherwise you might crush the process, which is probably not what you want to do.
Who has the next brave wink or nod? All right, we have one over here.
So just to confirm that, so there's no protection against process injection under OS X?
I haven't seen any. So on Windows, personal security products seem to do a decent job. I mean, to get by, say, Kaspersky, you can do it, but it takes a little work. I didn't see any personal security products blocking that. I didn't do extensive testing. Definitely they don't protect against the load time injection, which is you just dropping the dilib. But I didn't see any runtime injection protection either, but it could be out there.
There's no reason you couldn't implement that.
Yeah, I mean, it's just monitor. Again, there's no real, in my opinion, there's not a lot of legit reasons why process A is injecting or spawning a remote thread. So it just seems that a lot of the security tools on OS X, the third-party ones, are very, it's almost like where security tools on Windows were 5 years ago, 10 years ago. So they just don't think they've gotten there yet.
Can you share any more about the interactions with Apple and how they defended that stance?
Yeah, so for example, the gatekeeper bypass, I submitted it to bugreport.apple.com, didn't get a response, waited a month, responded again, got an automated response, followed up again, finally I got a thank you, because I told them I was going to be talking about it. I then did talk to Apple's security team, and they turned out to be awesome. They just said it was a miscommunication. I think they just have a very small team. I don't know though, it's like some of the concepts though, it's like verifying kernel mode signatures in user mode. It's like, this is not even a security check. Like, what? But it seems like they're slowly getting it. There's more Mac malware out there, stuff like that. So I'm optimistic, cautiously so, that they're trending in the right direction. But I think they just make so much money that they don't.